And now in this lecture we'll answer on two questions. In the first question we find out the area of this rectangle ABCD that blocks this circle, and in the second question we find out the area of this trapezoid ABCD. So we'll start with the first question. In the drawing we have rectangle ABCD, and this circle is inscribed by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this angle is a right angle. And we also know that the area of any rectangle equals to the length of the rectangle times the width. We define the length of this rectangle ABCD as AB. And we define the width of this rectangle ABCD as AD. We define the radius of this circle as R. Point O is the center of this circle, point M is the point of the circle itself, therefore OM is the radius of this circle, that is equals to R. So we join points O and M together by a straight line. OM is the radius of the circle, that is equals to R. The radius OM is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO, according to rule 1. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to rule 1. Likewise, we join points O and N together by a straight line. ON is of course the radius of this circle, that is equals to R. The radius ON, that is equals to R. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. Point E is the point of tendency of tangent DA with this circle. We join points O and E together by a straight line. OE is of course the radius of this circle, that is equal to R. The radius OE is drawn to point E, that is the point of tendency of tangent AD with this circle. And whenever your radius is drawn to the point of tendency, then tangent AD will be perpendicular to the radius EO. If AD is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, you get that the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees. according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4-piece angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOE we have 4 right angles, and so we continue with the lower quadrilateral EO and A. In the lower quadrilateral EO and A we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-piece angle in total must be equal to 360 degrees according to the sum rule. Therefore this 4-piece angle must be equal to 90 degrees in its size. So if we found out that the big angle MON is equal in total to 90 degrees plus 90 degrees, that is 180 degrees. So write it down. The big angle MON is equal to 180 degrees in its size. And we know that any angle is equal to 180 degrees in its size. It is defined as a straight line. So MON is a straight line. Line segment MON is a straight line. And if line segment MON is a straight line, then MN is also a straight line. But MN is a straight line that touches the circle at 2 points, point M and point N. And therefore MN is a chord. MN is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore MN is the diameter of the circle. So write it down. MN is a chord that passes for the center of the circle that is actually point O, and therefore MN is the diameter of the circle. MN is the diameter of the circle. MN is the diameter of the circle. So what to do? MN is the diameter. Anyway, MN is a diameter. It is absolutely a straight line. So in this shape D, M, and A, we have 1, 2, 3, 4 sides, and therefore shape D, M, and A is a quadrilateral because it has 4 sides, and it is a quadrilateral with 4 right angles, and therefore it is a rectangle. Okay. So quadrilateral D, M, N, A is a rectangle because it has 4 right angles. So write it down. The big quadrilateral D, M, N, A is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side DA equals to the opposite side MN. In rectangle DMNA, the opposite sides are equal to each other. That is to say, side DA is equal to the opposite side MN. According to our definition, DA is the width of rectangle ABCD, so I'll write it down. DA is the width of rectangle ABCD, and we already found out that MN is the diameter of the circle. So I'll write it down. MN is the diameter of the circle. In the next step, we will extend the radius EO, that is equals to R. We will extend the radius EO by a straight line until it touches the circle. So we extended the radius EO from point O by a straight line until it touches the circle at this point. We define the touching point of the extended radius EO with this circle, this point, as point L. EO is the radius of the circle, therefore it is absolutely a straight line. And we extended the straight line EO by a straight line, the result is EL. When you extend the straight line by a straight line, the result must be a straight line. So EL is also a straight line that touches the circle at points E and L. And therefore EL is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore EL is the diameter of the circle. So we can write in this equation that EL is the diameter of the circle. And from this long equation, the width equals to dA equals to MN equals to the diameter equals to EL. We will derive that EL is the width of rectangle ABCD. EL is the width of rectangle ABCD. In the next step, we will join points L and F together by a straight line. By joining points L and F, we create peripheral angle LFE. This is peripheral angle LFE that subtends on EL, that is the diameter of the circle, and we know that any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle LFE is equal to 90 degrees in its size according to rule 7. So, I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the domain, we have a circle. AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of the circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size. We have already implemented rule 7 in our drawing. One because in our drawing we have peripheral angle LFE that subtends on EL, that is the diameter of the circle, and therefore peripheral angle LFE must be equal to 90 degrees in its size according to rule 7. So in the right triangle ELF, we define this angle as alpha. So in the right triangle ELF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will extend the radius EL by straight. We will extend the diameter EL by straight line until it touches side CB of this rectangle ABCD. And we define the touching point of the extended diameter EL with side CB. This point is point T. By doing this construction, we created the big quadrilateral ETBA. Anyway, ET is definitely a straight line because the diameter EL is a straight line, and when you extend a straight line by a straight line, the result is a straight line. That is to say, ET is a straight line. So by doing this construction, we created the quadrilateral ETBA. Inside this quadrilateral ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th pieces angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th pieces angle must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least rectangle if not a square. So relate to the big quadrilateral ETBA is a rectangle because it has 4 right angles. So write it down. Quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So write it down. In rectangle ETBA, the opposite sides are equal to each other. That is to say, side ET must be equal to the opposite side AB. ET equals to AB. But according to our definition, AB is the length of rectangle ABCD. So we can write here that AB is the length of rectangle ABCD. And from this equation, ET equals to AB equals to the length. We derive that ET is also the length of rectangle ABCD. ET is the length of rectangle ABCD. So in conclusion, we should find out that EL is the width of rectangle ABCD and ET is the length of rectangle ABCD. In the next step, we will focus on the big right triangle, triangle ETG. On the big right triangle, triangle ETG, this angle equals to alpha according to our definition. This angle equals to 90 degrees. Therefore, this vertical angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So actually it is very easy to say that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. So I'll explain why those two right triangles are similar to each other. First of all, this is angle E that is also defined as alpha. That is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E also belongs to the big right triangle ETG. So angle E equals to itself. It's a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we will prove that all the figures of the big right triangle ETG are correspondingly equal to all the figures of the small right triangle ELF. And therefore those two right triangles are similar to each other according to angle similarity rules. So write it down. We also found out that the big right triangle ETG is similar, this is the sign of similar, to the small right triangle ELF according to angle similarity rule. Because again, if we found out that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle EFL is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. Okay, again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. Over EF. EF equals to 12 units in its length, according to what is given as the question. And it is equal to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so we leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here we will cross multiply this equation. And we get that ET times EL is equal to 22 times 12. So ET times EL equals to 22 times 12 is 264. So in total, we actually found out that ET times EL is equal to 264. But we have already found out that ET is the length of rectangle ABCD and EL is the width. So we substitute ET by the length of rectangle ABCD and we substitute EL by the width of rectangle ABCD. So in total we get that the length of rectangle ABCD times the width of rectangle ABCD is equal to 264 square units. And that is the answer to the first question. And again, if we found out that the area that we are looking for in this question, that is the area of this rectangle ABCD, is equal to 264 square units. So we finished with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our mission is to find out the area of this trapezoid ABCD. It is given as the question that AB equals to AP, PD equals to DC, BQ equals to 4, QC equals to 9. This is angle PQC, this is right angle. Those two angles are also right angles. Again, our mission is to find out the area of this trapezoid ABCD. So AB equals to AP according to what is given as the question. So if we define the length of this side AB as A, then the length of this side AP must be also equal to A, because they are equal to each other according to what is given as the question. Likewise, if we define the length of line 7 PD as B, then the length of line 7 of side DC must be also equal to B, because they are equal to each other according to what is given as the question. In the next step, we will join points B and P together by a straight line. And we will join points P and C together by a straight line. By joining points P and B, we created the right triangle, triangle PAB. This is a right angle, that is also a isosceles triangle. Why? Because side AP equals to side AB. We have the rule that says that in front of equal sides in a triangle, there are equal angles. So in front of those two equal sides, there are those two angles that must be also equal to each other, because they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in the right triangle ABP, this right triangle ABP, the sum of the angles must be equal to 180 degrees. It is true in any triangle, and especially it is true in this right triangle, triangle ABP. So which angles we have in the right triangle ABP? We have this angle that is 90 degrees, plus alpha is equal to 180 degrees. So already known. In the right triangle, the right small triangle, triangle ABP, the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus 2 alpha is equal to 180 degrees. So here we subtract 90 degrees from this equation, and when you get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we will divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So actually, this is angle alpha. The size of this angle alpha is 45 degrees. Likewise, the size of this angle alpha is also 45 degrees. We don't have to repeat on the same process in this right and associated triangle, triangle BDC, triangle PDC. It is a right triangle because this angle equals to 90 degrees, and it is an associated triangle because BD equals to DC. So you can write down immediately that this angle equals to 45 degrees, and this angle also equals to 45 degrees. Because we arrive to the same result here, we don't have to repeat again on the same proof in this triangle, triangle PDC. So, if we know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees, according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AD at point P? We have this angle that is 45 degrees, plus this angle that is also 45 degrees, in total it is 90 degrees. plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to 90 degrees in its sides. Why? Because 90 degrees plus 45 degrees plus 45 degrees, in total it is 180 degrees. That is the sum of the angles on the right side of the straight line AD at point P according to rule 3. So, if we define the size of angle BPQ, this angle is alpha, then this missing angle must be equal to 90 degrees minus alpha. It is very trivial because 90 degrees minus alpha plus alpha is 90 degrees, exactly the size of the big angle BPC. Therefore, this missing angle must be equal to 90 degrees minus alpha. So, in the right big triangle PQC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle PBQ, but before that, BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles you have at the left side of the straight line BC at point Q? You have this angle that is 90 degrees plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the right small triangle PQB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll prove that the small green right triangle PQB is similar to the big right triangle PQC. It is very easy to see it from the drawing, but I will prove it anyway. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually prove that all the three angles of the big right triangle PQC are correspondingly equal to all the three angles of the small right green triangle PBQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually prove that the big right triangle PQC is similar. This is the sign of similar to the right small triangle PBQ according to angle similarity rule. It is very easy to see that side PQ is a common side that belongs to the green small right triangle PBQ, and it is also side PQ also belongs to the big right triangle PQC. So side PQ is a common side that belongs to both triangles. So from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. So repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PBQ, side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. PQ is the missing side, so we leave it as it is. Over BQ equals to 4 units in its length according to what is given as the question, and it is equal to QC equals to 9 units according to what is given as the question. Over PQ is the missing side, so we leave it as it is. So in total we actually found out that PQ over 4 equals to 9 over PQ. Here we will cross multiply this equation and we will get that PQ times PQ is PQ squared. That is equal to 9 times 4 is 36. So PQ squared equals to 36. So we take a root out of this equation and finally we get that the missing side PQ is equal to the square root of 36, that is 6. So we found out that the missing side PQ is equal to 6 units in its length. So I write it down. PQ equals to 6 units in its length. In the next step, we will implement the Pythagoras theorem on the big right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the square of the perpendicular. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is the relation for Pythagoras theorem. The hypotenuse in the right triangle PBC is BC, so the square of the hypotenuse is BC squared. And it is equal to BP squared plus PC squared. So I can find out that according to the Pythagoras theorem, in this big right triangle BPC, BC squared, that is the square of the hypotenuse, equals to BP squared plus PC squared. What is the length of BC? BC in total equals to 4 plus 9, that is 13. Okay. BC equals to 13, therefore BC squared is 13 squared, that is 169. So BC squared is 169. And it is equal to BP squared. What is the value of BP squared? We will focus on the right small triangle ABP. On the right small triangle ABP, according to the Pythagoras theorem, we get that A squared plus A squared equals to PB squared. So A squared plus A squared is 2A squared. So PB squared equals to 2A squared. Plus PC squared. What is the value of PC squared? We'll focus on the right triangle PDC and we'll implement the Pythagoras theorem on this right triangle PDC. According to the Pythagoras theorem, this right triangle PDC, B squared plus B squared equals to PC squared. That is to say, BC squared equals to B squared plus B squared, that is 2B squared. So PC squared equals to 2B squared. So in total, we actually found out that 169 equals to 2A squared plus 2B squared. So 169 equals to, we take 2 out as a common factor out of those two expressions. Inside the brackets, we left only with A squared plus B squared. So in total, we actually found out that 169 equals to 2 times A squared plus B squared. Here we will divide this equation by 2, and finally we get that A squared plus B squared equals to 169 over 2. Repeat again. Found out that a squared plus b squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? Actually, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of the first component is the right triangle ABP. So it is the area of the first component, it is the area of the right triangle ABP. Plus the area of the second component is the big right triangle PBC. So it is plus the area of the second component, that is the area of the big right triangle PBC. Plus the area of the third component that trapezoid ABCD consists of. The third component is the right triangle PDC. So the area of the first component is the area of the right triangle PDC. So, I repeat again, I should found out that the area of this trapezoid ABCD, must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of this right small triangle ABP, so it is the area of this right triangle ABP. The second component is the area of the big right triangle PBC, so it is plus the area of the big right triangle PBC. That is the area of the second component, plus the area of the third component, that is the area of triangle PDC. Okay. So, in the first step, we found out the area of each component, and we will add the three areas together, and this will be the area that we are looking for, that is the area of trapezoid ABCD. So what is the area of the small right triangle ABP? This is the small right triangle ABP. Actually, the area of any triangle equals to the base of the triangle times the height over 2. The base is AB, the height is AP divided by 2. AB is A, AP is A. So AB times AP is A times A, that is A squared over 2. So we found out that the area of this right triangle ABP is equal to A squared over 2. Plus the area of the big right triangle PBC. What is the area of this big right triangle PBC? We choose the base as BC. So it is BC, the base is BC times the height. The height is PQ. Why the height is PQ? Because of the fact that PQ creates 90 degrees with the base BC. This angle costs 90 degrees. So the height is PQ over 2. So in total we actually found out that the area of this big triangle PBC is equal to the base BC times the height PQ over 2. Plus the area of the first component, that is the area of this right triangle PDC. The area of the right triangle PDC equals to the base DC times the height DP over 2. DC is B, DP is also B. So it is B times B, it is B squared over 2. So in total, the area of this right triangle PDC is B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. And we have BC times PQ over 2. BC, in total it is 4 plus 9, that is 13. Times PQ. PQ is 6 divided by 2. So in total, we actually found out that the area of trapezoid ABCD equals to A squared plus B squared over 2 plus 16 plus 13 times 6 over 2. We have already found out that a squared over b squared equals to 169 over 2. So we will substitute a squared plus b squared in this expression by 169 over 2. So a squared plus b squared is 169 over 2, and we have to divide it by 2. It is 169 over 2, and we have to divide it by 2. Plus 13 times 6 over 2. 13 times 6 over 2 is equals to 6 over 2 is 3, and 3 times 13 is 39. So in total, this expression equals to 39. So the area of trapezoid ABCD equals to 169 over 2 times 2. That is actually 169 over 2 times 2 is 4 plus 39. So here we will multiply 39 by 4, and then we will divide it by 4 in order to have a common factor with this number. So in total, in the numerator, we will have 169 plus 39 times 4 is 156 divided by 4. 156 plus 169 is 325 divided by 4. 325 over 4 is 81.25 square units. So if we found out that the area of trapezoid ABCD, that is the area that we are looking for in this question, is equal to either 325 over 4 square units, or in terms of numbers, it is equal to 81.25 square units. And that is the answer to the second question. Repeat again, we shall find out that the area that we are looking for in this question, that is the area of this trapezoid ABCD, it is equal to either 325 over 4 square units, or in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. So we finished with the second question. In the next step, we'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this rectangle ABCD. Rectangle ABCD blocks this circle, or this circle is inscribed by rectangle ABCD. We also know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside any rectangle are right angles. So the missing angle here is equal to 90 degrees in its size. We define the length of rectangle ABCD as AB and the width as DA. And you know that the area of any rectangle equals to the length of the rectangle times the width. Okay, so we define the radius of this circle as R, and we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together by a straight line. ON is the radius of this circle, that is equals to R. The radius ON, that is equals to R. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius AO, to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to the same rule, rule 1. In the next step, we join points O and E together by a straight line. O is the radius of this angle, that is equal to R. The radius OE that is equals to R is drawn to point E, that is the point of tendency of tangent AD with this circle. And whenever your radius is drawn to the point of tendency, then tangent AD will be perpendicular to the radius EO. If AD is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to the sum rule, all 1. By doing this construction, we get the quadrilateral DMOE. Inside quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-fifths angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4-fifths angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral EONA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-fifths angle, in total must be equal to 360 degrees, according to the sum of the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4-fifths angle must be equal to 90 degrees in its size. So in the big right angle, in the big angle MON, this angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So the big angle MON is equal to 180 degrees in its size. And we know that any angle is equal to 180 degrees in its size, it is defined as a straight line. So MON is a straight line. If MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle at 2 points, M and N. Therefore, MN is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. MN is the diameter. MN is the diameter of the circle. Anyway, MN is the diameter. It is absolutely a straight line, and therefore this shape DMNA consists of 4 sides. 1, 2, 3, 4. Therefore, it is a quadrilateral. It is a quadrilateral that has 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle and flat square. So, related to the big quadrilateral DMNA is the left angle according to rule 5, because it has 4 right angles. So, we know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Repeat again. In the big rectangle DMNA, side MN must be equal to the opposite side DA. But according to our definition, DA is the width of rectangle ABCD. So you can write here that DA is the width. And we just write the formula that MN is the diameter of the circle. So you can write here that MN is the diameter. In the next step, we extended the radius EO by straight line until it touches the circle at this point, point L. We define the touching point of the extended radius EO with this circle. This point is point L. EO is a radius, it is a straight line. When you extend a straight line by straight line, the result must be a straight line. So EL must be also a straight line. EL is a straight line that touches the circle at 2 points, E and L. Therefore, EL is a chord. EL is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, EL is also the diameter of the circle. Here, EL is the diameter of the circle. So we can write here that EL is also the diameter of the circle. EL is the diameter. And from this long equation, the width equals to DA equals to MN equals to the diameter equals to EL. We will derive that EL is the width of rectangle ABCD. EL is the width of rectangle ABCD. Okay. So in the next step, we join points L and F together by a straight line. By joining points L and F, we created peripheral angle LFE. This is peripheral angle LFE that subtend on LE, that is the diameter of the circle, and we know that any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees in its size. Therefore, according to rule 7, this peripheral angle LFE must be equal to 90 degrees in its size. So in the right angle LFE, we define this angle as alpha, this angle is 90 degrees. So this angle is alpha, according to our definition, this angle equals to 90 degrees, and therefore this surface angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. In the next step, we extended the diameter EL by straight line until it touches side CB of this rectangle ABCD. We define the touching point of the extended diameter EL with this side CB. This point is point T. Actually, ET is definitely a straight line because EL is the diameter that is definitely a straight line, and we extend a straight line by straight line. The result ET must be also a straight line. So ET is one straight line. Therefore, this shape ETBA is a quadrilateral because it has 4 sides. 1, 2, 3, 4. And inside the quadrilateral ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of the square. So we left to the big quadrilateral ETBA is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. Repeat again. In the big rectangle ETBA, side ET must be equal to the opposite side AB. But AB, according to our definition, is the length of rectangle ABCD. So you can write here that AB is the length of rectangle ABCD. And from this equation, ET equals to AB equals to the length of rectangle ABCD. We will derive that ET is also the length of rectangle ABCD. So in total, we found out that EL is the width of rectangle ABCD and ET is the length of rectangle ABCD. Okay, so in the next step, we focus on the big right triangle ETG. The big right triangle ETG, this angle equals to 90 degrees, and this angle equals to alpha according to our definition. This angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So it is very easy to see that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity. So I will prove it anyway. Why those two right triangles are similar to each other. First of all, this is angle E that is also defined as angle alpha. It is a common angle that belongs to both triangles. So we can write down that angle E equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I found out that all the three angles of the big right triangle ETG are correspondingly equal to all the three angles of the small right triangle ELF. And therefore, those two right triangles are similar to each other according to angle similarity rules. So I write it down. So I'll repeat again. We actually found out that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So repeat again. We derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF equals to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. over EF. EF is equal to 12 units in its length according to what is given in the question. And it is equal to EG. EG in total is 12 plus 10, that is 22 over EL. EL is the missing side, so we need to set it. So in total, we should find out that ET over 12 equals to 22 over EL. Here we first multiply this equation and finally found out that ET times EL equals to 22 times 12. So ET times EL equals to 22 times 12, which is 264. So in total we found out that ET times EL equals to 264. But we have only found out that ET is the length of the rectangle ABCD and EL is the width. So the substitute ET by the length of rectangle ABCD and the substitute EL by the width of rectangle ABCD. So in total we found out that the length of rectangle ABCD times the width of rectangle ABCD is equal to 264 square meters. So again we found out that the area of this rectangle ABCD is equal to 264 square meters. So we finish with the first question. In the next step I presented to you the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. So in the drawing we have trapezoid ABCD, side AB equals to 97 AP, 97 PD equals to side DC, BQ equals to 4, QC equals to 9. This is an angle PQC that is right angle. Those two angles are also right angles. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, AB equals to AP according to what is given as the question. So, if we define the length of side AB as A, then the length of side AP must be also equal to A because they are equal to each other according to what is given as the question. Likewise, PD equals to DC. So if we define the length of side PD as B, then the length of side DC must be also equal to B because they are equal to each other according to what is given as the question. In the next step, we join points B and P together by straight line. We join points B and C together by straight line. By joining points B and P, we get the small right triangle BAP. We have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other on their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other, according to the rule that I mentioned. So if this angle is alpha, then this angle is also alpha. So in the right triangle ABP, the sum of the angles must be equal to 180 degrees. So which angles we have in the right small triangle ABP? We have this angle that is 90 degrees. Plus alpha, in total must be equal to 180 degrees. So 90 degrees plus 2 alpha must be equal to 180 degrees. Here we supply the 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 degrees. So this is again alpha that is 45 degrees, and this is also again alpha that is 45 degrees in its size. So we actually found out that if we have a right triangle that is also an associated triangle, it always has the same three angles. One angle is a right angle, and the other two angles must be equal to 45 degrees, each of them. So in this right and associated triangle PDC, this angle is 90 degrees, and therefore the other two angles must be equal to 45 degrees in their sizes, each of them. We don't have to repeat on the same process in order to prove that those two angles must be equal to 45 degrees. Because it is exactly the same proof like we did here. So, if we know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P here, the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? We have this angle that is 45 degrees plus this angle that is also 45 degrees. So 45 degrees plus 45 degrees is 90 degrees. So 90 degrees plus the size of this fourth missing angle in total must be equal to 180 degrees according to all three. Therefore, this third missing angle must be equal to 90 degrees in its size. That is to say, the big angle BPC must be equal to 90 degrees in its size. Why put 90 degrees plus 45 degrees plus 45 degrees? It is equal to 180 degrees. That is the sum of the degrees on the right side of the straight line AD at point P according to all three. So this missing angle BPC must be equal to 90 degrees in its size. So if we define this angle that is actually angle BPQ as alpha, then this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is exactly the size of the big angle BPC. So this missing angle must be equal to 90 degrees minus alpha. So in the big right angle PQC, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees. Therefore, this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in the triangle. Likewise, in the great small triangle BPQ, this angle equals to alpha. Actually, this angle equals to 90 degrees according to all three. So, I repeat again, BC is one side of trapezoid ABCD, it is absolute straight line. So if you focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees. So which angles we have at the left side of BC at point Q? We have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. So in the right great triangle BPQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. In the next step, we prove that the range small triangle PBQ is similar to the big right triangle PQC. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So I can prove that all the triangles of the big right triangle PQC are correspondingly equal to all the triangles of the small green triangle PBQ, and therefore those two right triangles are similar to each other according to angle similarity rule. So if we prove that the big right triangle PQC is similar, this is the sign of similar to the small right triangle PBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. And again, we derive that PQ of BQ equals to QC over PQ. PQ is the missing sides of related cities, BQ is 4, QC is 9, PQ is the missing sides of related cities. So in total PQ over 4 equals to 9 over PQ. Here we cross multiply this equation and finally found out that PQ times PQ is PQ square is equal to 9 times 4, that is 36. So PQ square equals to 36. We took out of this equation and finally found out that PQ equals to the square root of 36, that is 6. In the next step, we implemented the Pythagoras theorem on the right big triangle PBC. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right big triangle PBC, the hypotenuse is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus BC square. Repeat again, in the right triangle PBC, according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, equals to PB square plus PC square. BC in total equals to 4 plus 9, that is 13. Therefore BC square is 13 square, that is 169. Here BC square is 169, and it is equals to PB square. In order to find out the value of PB square, we implemented the Pythagoras theorem on this right triangle APB. According to the Pythagoras theorem, on this right triangle APB, a square plus a square equals to PB square. A square plus a square is 2a square. So PB square equals to 2a square again PB square equals to 2A square plus PC square. What is the value of PC square? In order to find out the value of PC square, we represent the Pythagoras theorem on this right triangle PDC. According to the Pythagoras theorem on this right triangle PDC, B square plus B square equals to PC square. So PC square equals to 2B square. So again, PC square equals to 2B square. So in total, we should find out that 169 equals to 2A square plus 2B square. So 169 equals to, here we took 2 as a common factor out of this expression, so inside the brackets we left only A square plus B square. So 169 equals to 2 times A square plus B square. Here we divided this equation by 2 and finally found out that A square plus B square equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. What is the area of trapezoid ABCD? The area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of this right triangle ABP. The second component is the big right triangle BPC, and the third component is this right triangle PDC. So the sum of the areas of those three components in total they must be equal to the area of the big trapezoid ABCD. Okay, again, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. Those are the three components that trapezoid ABCD consists of. So the sum of the areas of the three components is the area of trapezoid ABCD. So what is the area of the first component? That is the area of triangle ABP. So what is the area of triangle ABP? The area of pentagon equals to the base of the triangle times the height over 2. The base is AB, that is A. The height is AP, that is also A. So it is A times A, that is A square over 2. So the area of triangle ABP is A square over 2. Plus the area of the second component, that is the big triangle PBC. What is the area of the big triangle PBC? It is equals to BC, that is the base, times the height, that is PQ over 2. So in total, the area of the big triangle PBC is equals to BC times QP over 2. Okay, again, the area of the right big triangle PBC equals to the base BC times the height PQ over 2. Plus the area of the third component, that is the area of this right triangle PDC. The area of this right triangle PDC equals to the base DC times the height TP over 2. So it is B times B over 2, that is B square over 2. So the area of the right triangle PDC is B square over 2. And we have here A square over 2 plus B square over 2 is A square plus B square over 2. BC in total is this 4 plus 9, that is 13, times PQ is 6 over 2. And again, BC is 13, PQ is 6 divided by 2. So in total, the area of trapezoid ABCD equals to A square plus B square over 2 plus 13 times 6 over 2. So A square over B square is equal to 169 over 2. So we substitute A square plus B square in this expression by 169 over 2, and we have to divide it by 2. Plus 13 times 6 over 2 is 6 over 2 is 3, and 3 times 13 is 39. So in total, this expression equals to 39. So the area of trapezoid ABCD equals to 169 over 2 times 2 is 4. So it is 169 over 4 plus 39. Here we multiplied 39 by 4 and then we divided by 4 in order to become factor with this number. So in total, the numerator we have 169 plus 39 times 4 is 156 divided by 4. 169 plus 156 is 325 over 4. 325 over 4 is 81.25 square units. So in total, we should find out the area of this trapezoid ABCD, that is the area that we are looking for this question, is either equals to 325 over 4 square units. So in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.